Good day everyone. We are the group 8 and our topic is all about graphs in algorithms. So before we start, here are some of our contexts of our presentation. So first, what is graph? Vertices and edges. Second, what are the kinds of graph? Third, what is graph coloring? Fourth and fifth, adjacent matrix and adjacent list. And the 6 and 7 is depth first and breadth first search. So let's start. So what is graph? Graph is a pair of V and E, where the V is a set of vertices and the E is a set of edges. So here are the examples. In the diagram of a graph, a vertex usually represented by a circle with a label, and an edges is represented by a line or arrow extending or connecting from one vertex to another. So the next is, what are the kinds of graphs? So here are the examples.
Directed graph, the order of the vertex in the pairs in the edge set matter. A directed graph or digraph is a set of nodes connected by edge, where the edge have a directed associated with them. Another kind of graph is undirected graph. In an undirected graph, the order of the vertex in the pair's edges set doesn't matter. The edges may be directed or undirected. For example, if the vertex represents people at the party and there is an edge between two people if they shake hands, then this graph is undirected because any person A can shake hands with a person B only if B also shakes with A. Another kind of graph is cycling graph. A cycling graph is directed graph with at least one cycle is apart along the directed edges from a vertex to itself. The vertex level graph above us has several cycles. The relationship between nodes in a graph can be represented with an adjacency matrix or an adjacency list. Both represents directed edges. A connection between two nodes is a one-way relationship. Next, the directed acycling graph or DAG. They call it DAG. A DAG is directed graph with cycles. Example of a DAG. Theorem every finite DAG has at least one source and at least one sink. In fact, given any vertex V, there is a path from some source V and a path from V to some sink. Next is proper graph. A proper graph is a graph which has no cycle and not more than one edge.
Graph coloring. Graph coloring is a special case of graph labeling. It is an assignment of labels, traditionally called colors, to elements of a graph subject to certain constraints. In its simplest form, it is a way of coloring the vertices of a graph such that no two adjacent vertices share the same color. This is called a vertex coloring. Similarly, an edge coloring assigns a color to each edge so that two adjacent edges share the same color, and a face coloring of a planar graph assigns a color to each face or region so that no two faces that share a boundary have the same color. Sa graph coloring po, explain ko lang po, hindi po pwedeng sa graph magka-connected yung dalawang parehas na kulay. Ito po yung example ng graph coloring. Papaliwanag ko po yung planar and non-planar. Yung planar po, magko-connect lang siya sa mga vertices ng edges. Tapos yung non-planar po is pwede siyang kumonect pero sa mga edges at vertices lang.
Adjacency matrix. A two-dimensional matrix in which the rows represent source vertices and columns represent destination vertices. Data on edges and vertices must be stored externally. Only the cost for one edge can be stored between each pair of vertices. Adjacency list. Vertices are stored as record or objects. In every vertex, store a list of adjacent vertices. This data structure allows the storage of additional data on the vertices. Additional data can be stored if edges are also stored as objects, in which case each vertex stores its incident edges and each edge stores its incident vertices.
Good day everyone. Today we will talk about depth first search and breadth first search. The first one is depth first search. First, we must keep track of our stack status and output. We will start alphabetically. Let's visit our first node, which is the letter A. It has its two adjacent and visited node, letter V and S. We will mark the node A as our visited node. Next, we will proceed to visit node V and mark it as a visited node. The node B has no adjacent and unvisited node, so we will remove it from our stack status. Remember, we will start our list of the stack status of the bottom. Next is the node S. We will mark it a visited node and proceed its adjacent and visited nodes C and G, but we are doing alphabetically, so we go for node C. Mark node C as visited node and proceed to node D. Mark node D as visited. Node D has no adjacent and visited node, so we will proceed to visit mark node E and remove node D from the stack status. Node E has adjacent and visited node, which is the node H. Node H has an adjacent and visited node, which is a node G. We'll mark it has a visited node. And lastly, we proceed to our last adjacent and visited node of node G, which is the node F. Mark node F as a visited node. Since there is no more to visit, we must remove F from our stack status and we are finished. The next one is breadth first search. First, we have to keep track our steps with the help of our queue status and output. Let's start at our first node, which is the node A. This will be our current node and we proceed to our adjacent and visited node with the node B. Next, we proceed to our next adjacent and visited node, which is node S, and then we will change our current node to B. And we proceed to our next adjacent and visited node with each node C, and then we will change our current node to S. And we proceed to our next adjacent and visited node, which is node G, and then we will change our current node to C. And we proceed to our next adjacent and visited node, which is node D, and we will change our current node to G. And we proceed to our next adjacent and visited node, which is node E, and then we will change our current node to D. And we proceed to our next adjacent and visited node, which is node F, and then we will change our current node to E. Lastly, we proceed to our next adjacent and visited node, which is node H, and then we will change our current node to F. And that's all of our presentation graph algorithms.